Next up, Allan Sly from Berkeley will tell us about rapid mixing of Gibbs sampling on graphs that are sparse on average.
What? Did you have to wave anymore?
Okay. Thank you. And so this is joint work with Elkanan Mosul. So most of the, well, essentially all the definitions have been that I'll need for this talk have been said several times already in the last 2 days. So I'm not going to tell you what a colouring is again, but so I'll be looking at the Glauber dynamics on Gibbs measures like colourings, and they were defined, the sorts of techniques were defined specifically with colourings in mind, although they work more generally for other Gibbs measures. So in particular for the easing model or the hardcore model or any other models with soft constraints, we have results. But I'll talk specifically about colourings. And we'll be looking at the Glauber dynamics, which I won't define again. And so in a lot of the previous talks, the results have been of the form, the mixing time is n log n in the number of vertices of the graph. And in this case, so for reasons that I'll explain later, I'll be mainly interested in showing just polynomial mixing times in the number of vertices, because n log n mixing won't be true. And yesterday, Eric gave us an excellent sort of summary of all the results done by many of the people at this workshop on results of mixing of colourings on graphs, starting from Jérôme and using increasingly sophisticated coupling methods. So I won't say any more about them, except to make the observation that they all depend on the maximum degree of the graph. And so but for some models of graphs, the maximum degree isn't necessarily the most important parameter, and there can be a lot of inhomogeneity of the degrees of the graph, and so the maximum degree may be very different from the typical degree. So we'd like to prove results which depend more on the typical degree instead. So a first naive question you might think of is, can we do something in terms of the typical or average degree? And the answer is very clearly no. So for a start, there may be no colourings, or the Markov chain may not be ergodic. But even in something like the easing model, where these aren't issues, if you take, say, a star on n vertices, then the mixing time is exponential in n, even though the graph has average degree 2. So to get anywhere, we'll need a few more conditions on the graphs. And the model of graphs we had in mind were Erdős-Renyi random graphs. So you take n vertices and connect each pair of vertices with probability p. And we'll want to maintain a constant average degree as n grows, so we'll let p equal d over n. And Erdős-Renyi random graphs have been very extensively studied. So some standard properties which hold asymptotically almost surely. When d is greater than 1, you have a giant component of linear size in n. This will be the case that we'll be interested in, because when d is less than 1, all the components are small and are almost tree-like, and then the mixing will be sort of obvious from that. The graph is locally tree-like, so if you choose a random vertex with high probability, it'll look like a tree. And in fact, if you choose any vertex and look at the neighborhood of radius approximately a half log base d of n, you'll get a tree plus at most a bounded number of edges, where the bound is independent of n and the vertex you chose. So it's really very tree-like. And most importantly, for the context of this talk, the maximum degree grows like log n on log log n. So as a result, none of the previous results apply to these graphs, because when you're just dealing with a constant number of colors. So there's been some work on mixings of colorings on these graphs. Dyer, Flaxman, Fries, and Vigoda showed that when you have that to get n log n mixing, you need something a polynomial or polylog number of colors. But if you take the certain small blocks and look at the block dynamics with these correctly or well-chosen blocks, then you get n log n mixing of the block dynamics with log log n on log 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 n number of colors. And so this is still going to infinity with n, but at a much slower rate than the maximum degree. But the question we wanted to, so a question they posed and what we wanted to answer was, does the Glauber dynamics mix in polynomial time if you just have some large constant number of colors? So some function of just d alone and independent of n. So one immediate observation is that the mixing time will be greater than n polylog n, which you can prove from the fact that with high probability the Erdős-Renyi random graph will contain a star with order log n on log log n number of vertices, and you can directly analyze the mixing time of on stars and show that the mixing time is exponential in the number of vertices, and this gives you a lower bound greater than n polylog n. So the big technical hurdle is taking care of the occasional vertices with very high degrees, and there's one other thing is that you can't assume, while it's usually locally tree-like, there may be a few triangles and other small cycles within the graph, and they need to be taken care of too. But the result is that when you have sufficiently many colors, then you get polynomial mixing time of the Glauber dynamics on asymptotically every graph. Analogous results exist for the Ising model and the hardcore model, and other models with soft constraints. We haven't really looked at how this constant varies with d. So Eric yesterday had 1,000 d, but if having a quick look at the proof, I think we, without trying to do any extra work, we'd need something like 1,000 d to the 4, but still a constant in terms of d.
Your 1,000 doesn't depend on d.
Yeah.
Can I ask another question in understanding this? When you say mixes in polynomial in n time for almost asymptotically almost every graph, you mean that there is one polynomial in n that serves for almost all?
Yes. The polynomial, no, sorry, there's one polynomial for each fixed d.
Yes, but the polynomial doesn't vary from instance of the random graph to another.
No, that's right. Yeah. And I should mention that Spirakis and one of his students also, at the same time as us, did work on approximately sampling random colorings on Erdős-Renyi random graphs using a completely different techniques, a belief propagation type approach. Okay, so our results, the way we prove it is to say that with high probability, Erdős-Renyi random graphs have two key properties, and then say that all graphs with these properties obey a certain polynomial mixing time bound. So the first one is that if we take any vertex in the graph V and look at a radius of a log n for some small enough a, then what we get is a tree plus some bounded number of edges. So at most k extra edges. And the second condition is more technical. So for some, but what it essentially says is that if we look at any path in the graph, there aren't too many vertices too close to the path. So more specifically, we have some constant alpha between 0 and 1, and take the maximum over all paths of length less than or equal to a log n of the sum over all vertices u in the path, all vertices v in the graph, of alpha to the power of the distance from u to v, where this is the distance within the graph. And we need this to be less than c log n for some constant c. And so this is weighting so vertices close to a path contribute much more to the sum, and as they're further and further away from the path, their contribution to the sum decays exponentially. And you can show that with high probability, for some constants a and c, which will depend on d, Erdős-Renyi random graphs satisfy this condition too. And so for sufficiently many colors, depending on a, k, c, and alpha, the Glauber dynamics mixes in polynomial time for some polynomial depending on a, k, c, and alpha. Okay. And so the proof is then by a block dynamics argument, and it involves choosing blocks with nice properties. And we only use these two properties in order to construct the blocks. So we define the notion of a good vertex as u in terms of parameters alpha and epsilon if the sum over all vertices v in the graph of alpha to the power of the distance from u to v is less than epsilon. So this is saying that there aren't too many vertices too close to u. And in particular, it says that the degree of u can't be more than epsilon on alpha. And this condition on paths says that not too many, that if we take epsilon to be large enough, says that most of the vertices along a path must be good vertices. And so we partition the graph as follows. If we, so vertices that aren't good are called bad, and we can partition the bad vertices by saying two bad vertices are in the same block if there's a path joining them that doesn't have two consecutive good vertices in it. And this partitions the bad vertices into blocks, and we can and you can check that this is an equivalence relation. And so and to these blocks of bad vertices, we can add any adjacent good vertices, and a good vertex will only be adjacent to one of them. And if we have a good vertex that's only adjacent to other good vertices, we can make it its own block. And this condition is enough to show that for any positive L, if we take epsilon large enough, then the block diameters will be at most L log n. So this gives us a way of constructing blocks that aren't too big and have boundary vertices which are all good. Okay, so we also want to make sure that it's also going to be convenient if internal cycles are not too close to the boundaries of blocks. So I'll just say that we can split up the small internal cycles in the graphs so that into skeletons, or what we call skeletons, so that these subgraphs don't have too large degree. They contain all the small cycles within the graph, and they're reasonably well separated. Otherwise, we'd just join them up. And this is where we use this locally tree-like condition. And so to make sure that none of these cycles are too close to the boundary of a block, we can just join these blocks we constructed together so that they cover all of these blocks. And so our final blocks have the following, what will be nice properties. They're either a tree or a tree plus at most k extra edges, and any internal cycles are a long way from the boundary of the block. Blocks meet at most one edge. Their diameter is logarithmic, and finally, and most importantly, all the boundaries are good vertices. Okay, and so we're going to use these blocks to do a block dynamics argument. So the first observation, and I'm not going to prove this because it's just calculations, is that if you take a block and condition on the colors on the rest of the graph, it has only a small effect on the marginal colors on each of the vertices inside the block if we have sufficiently many colors. So if we take the number of colors to be sufficiently large, the sum of the conditional color given the boundary condition minus the uniform distribution can be made arbitrarily small.
Can you return to that? So what is the assumption on U? It's just U is right near the boundary?
How does beta decay with the distance to the boundary?
This is uniform over all vertices. So there'll be, if it's next to the boundary, there may be a few colors which it can't take, say, but though.
When you say for arbitrarily small, you're letting Q grow.
Yes. Yeah. Yeah. So we have, but Q will just depend on the constants we had before. So this will be So Q will be independent of the degree of D, say.
It will depend on this target beta.
Yeah, right. Okay. And so the argument is a block dynamics argument, which we've heard about a couple of times already at this workshop. So the block dynamics, again, is where you choose a block at rate 1, delete its spins and update it conditional on the distribution of the rest of the graph. Okay, so from now on I'll be talking about the dynamics where you update sites at rate 1, so the continuous time dynamics. And the relaxation time of the block dynamics, there's the key lemma we'll be using is that it's bounded. This gives us a bound on the relaxation time of the Glauber dynamics. So the relaxation time of the block dynamics times the maximum of the relaxation times on the blocks bounds the relaxation time of the Glauber dynamics. And so if we can bound each of these by polynomials, then we can get a polynomial bound on the relaxation time of the Glauber dynamics, and that will give us a polynomial bound on the mixing time. Okay, so we need to bound the relaxation time of the blocks, and this, so a lot of our blocks are trees, so this is the first example, and we use a further block dynamics argument. So choose a root for our tree, and take blocks as the root and its subtrees. Now the block dynamics the relaxation time of the block dynamics on this graph can be equated to the relaxation time of the Glauber dynamics on the root plus its neighbors, except where this isn't quite the coloring Gibbs measure. It's the coloring Gibbs measure given an external field, which is the effect from the boundary conditions. But because the effect of the boundary conditions is small, we can still, it's close to what we get, just the relaxation time for colorings on a star. And so it's exponential in the degree. And then applying the block dynamics lemma inductively, so the subtrees are also trees, so we can split them up into further blocks. Then we get a bound on the relaxation time of the whole tree, which is e to some constant times m of t, which is the maximum of the sum of the degrees of any path from the root to the leaves. And this we can bound by our assumptions. So this as logarithmic in n, and so this gives us a polynomial bound on the relaxation time on these trees. Some of our
And then just return to that last slide.
Yep.
Does this bound also follow from the general bound in terms of path width? This time is always.
Can you probably?
Allan was also a co-author on that one.
Yeah. This turned out to be easier, I think.
But this inequality as it stands is exactly given by path width is controlled by.
Okay, then yes. Okay, and but the more complicated graphs may look like small cycles, so with maximum degree k, plus trees hanging off them. And so we use the block dynamics argument once again to handle this. And so each vertex in the purple set with the cycles and the tree that's hanging off it is its own block. And the argument from the previous slide bounds the relaxation time of them. The relaxation time of these this internal cycle is you can just bound because this is the block dynamics is equivalent to a Glauber dynamics on this graph, and that's and it's a graph with bounded degree. So this gives the polynomial bound on the relaxation time on the blocks. So all that remains is to bound the relaxation time of the block dynamics, and this can be done just by a path coupling argument. So we can just, by using the path coupling method, we just reduce to the case where there's a single disagreement and look at the expected change in the number of disagreements. There can only be extra disagreements if the disagreement occurs at the boundary of a block and therefore at a good vertex. And so we'll get more disagreements if this is disagreements at a boundary vertex and we select a block adjacent to it. And then close to the boundary, it's very tree-like, and so when we update this block, the disagreement would have to propagate through this tree, and because we know that the marginal distribution of each of these, or the marginal colors of each of these vertices is close to the stationary distribution and can make arbitrarily close, then the probability that a disagreement propagates is some beta to the power of the distance from u to v. And then if beta is less than alpha, then we get the sum of beta to the distance of u to v is just less than epsilon times beta on alpha. And if we take beta sufficiently small, then the disagreements created will be sufficiently small, and this will give us a contraction of the path coupling and a bound on the mixing time of the block dynamics, which completes the proof. Okay, thank you.
Question? The work of Spirakis, the student, was it based on a randomized, a deterministic algorithm? Say the leaf propagation?
Randomized algorithm.
Yeah.
It doesn't give a deterministic response. That would matter.
Yeah. I don't think so.